So today's topic, just 4 of them. We'll start out with an introduction to reality capture. Hopefully those on the call here don't already know a ton about this, otherwise you might be a little bored to start with, but we need to make sure we're all on the same page before we dig a little deeper. We'll then talk about one of the biggest challenges that's faced by people working with point clouds, which is the reality versus design models, and a discussion of really what accuracy means and how to interpret that on a project. Then we'll get into a little deeper of how to work with the point clouds effectively. So for those that don't know, a few years ago we used to call what we did was just laser scanning. Now we tend to call it reality capture because it encompasses more than just laser scanning. It also now, the 2 primary things are still going to be laser scanning, but also photogrammetry is really taking hold, and this is turning 2D photographs into 3D point cloud data. The accuracies on that are getting better and better, and it's much faster to acquire than laser data. It's clearly the future. It's not there yet for most projects. We also have other types of data we capture as well. So we've sort of lumped all this together into reality capture. So today we're going to mostly focus on laser scanning. And when we start to talk about that, one of the first things we should touch on is that I think everyone at this point who's seen point clouds probably knows that they sort of come in 2 formats, color and black and white or grayscale. The grayscale is the data collected by the laser, and then it's supplemented or can be supplemented by photographs that color map to the points. So in what we do, there's all kinds of different equipment out there. This is obviously where we're seeing a lot of change and things are fluctuating. We still have the traditional laser scanners, and those sort of fit this nice middle ground of they're accurate enough, they're very fast, and they have long range, or reasonably long range. When we get into some of the aerial photography we do with drones and other means, the accuracy drops off, but the capture speed becomes incredibly fast. We're talking acres and acres of data per day that's captured, and extremely high ranges. It's just you're losing some of the detail. There are different types of scanners out there on the market that serve different needs. For example, there's some that can capture data at extremely long ranges and hold very tight tolerances, but you trade off speed to get that data capture. And then there's several more different types of units that are coming on that sort of merge LiDAR with photogrammetry with sensor units to produce kind of real-time data coming in as you move through a space. And again, these are interesting tech. They're not appropriate for a lot of jobs yet, but they're definitely making progress. So sort of when we talk about reality capture and how we do it, it breaks down to 4 primary steps. Step 1 is we plan it out. Step 2, we go on site and actually complete the work, the scanning work. Then we do the registration work, and then we create the outputs. What's important here to remember is that if we spend a couple days on site scanning, it's at least a couple days or sometimes more back in the office to get the final outputs produced. So on-site scanning, some things to keep in mind. Each scan is going to take 5 to 15 minutes. Expect 4 to 5 scans per 1,000 square feet, but this varies. Of all things we do, this varies the most depending on your structure and your site. It can go much higher and much lower. Best to scan when the site is inactive. Anyone who's worked with point clouds knows that you see people moving through the space. The scanners capture that movement. Depending on the size of the project, you may or may not need targets. This is an important distinction because having those targets is going to slow the project down, take more time to get them deployed, more equipment to deliver to the site. And then permanent targets, if you want to go back and you want to track a site over time, maybe you have an active construction site, you're going to want permanent targets installed so that you can have reliable data across multiple trips. The registration process, again, for those that don't know, is stitching the individual scans together into a point cloud. So each scan is just where the scanner sat and where it ran and took data from. We have to take all those individual scans, and you can see that in the image down below. Each of those purple dots is a scan, and stitch it together into one point cloud. As the registration comes together, we need to align the data. This is another thing we hear a lot from people, that the data they get doesn't match their existing CAD drawings, or it's rotated, or it's not level. This all happens in this alignment and registration step. By default, the alignment is whatever direction the first scan happened to be pointing. That needs to be shifted and brought into location. Typically, we're matching an existing CAD file of some kind, whether that's a Revit file, AutoCAD file. When we don't have that, we're typically just matching up a building corner and squaring it up, getting it pointed north. We're then going to create our output formats. There's a lot of different formats now that can come out. In general, though, they fall into three types. Point data, which is what everyone is typically used to. This is the actual point cloud data, just XYZ coordinates of points. You can have CAD data, which is derived from the point cloud. A lot of different ways you can make that. Or report data, we're seeing more. Report data is something, it could be the heat map like you see there on the right, or any other type of data that's being produced. It's not CAD or point cloud. So another thing for anyone who's new in scans that we run into is a lot of people see a picture like this, which is a scan, and they don't understand why it is fundamentally different than CAD. Even though this really looks great and it looks like a photograph, it's actually not. It's individual dots. Those dots can't necessarily be used to create design documents or any kind of derivative CAD work. They can be created in sort of a hybrid environment, but in general, if you're doing a lot of work, you need to convert this to CAD so you can produce clean drawings. Even though we're going to talk a little bit about ways around that in a little bit, but in general, it's important to remember that it is different, right? So this is a scan converted to CAD. You have point data versus vector data. The CAD file is going to work just like you would expect. You're going to be able to section it, cut it, do all these types of things, and create derived work from it. One thing, and we're going to touch more on this as we continue through here, point cloud data is big, and for anyone who's not used to working with it, before you get into it, you should have some kind of plan for dealing with that. If it's your very first time working with point clouds, consider having someone develop a CAD model for you. That's going to be a lot easier to work with for your first project or projects than working with the point cloud natively. So I'll talk a little bit about outputs in CAD and BIM world. And surprisingly, this whole presentation is about how to effectively work with point clouds. We're not actually going to talk much about how to work with them within Revit and AutoCAD or any other CAD software. And that's because it's extremely easy to do that. In Revit, they simply attach, as you would expect, any other link to work. You add them into your file. They're simply there. They respond to sections, elevations, plan view cuts, view ranges, all the usual stuff. They just exist within Revit, and you can simply trace over top of them. There's really not much to learn or to even talk about with that. In AutoCAD, same thing. They attach just like an XREF would attach. There are tools in AutoCAD that do let you section the point cloud, do clipping, but very, very basic stuff. You get into MicroStation or some of the other products that are out there, again, it just attaches like a reference and works as you would expect it to. Same in Navisworks and any of the other AutoCAD-derived applications. And I mentioned before, this is an important discussion to have on projects, especially it should be an ongoing one as projects evolve. And what we're going to talk about in here is understanding the difference between the accuracy captured by a laser scanner and what before laser scanners was considered acceptable accuracy within design and engineering documents. So single scans, again, this can vary by equipment, but single scans are going to be plus minus a millimeter accuracy, roughly, again, depending on the equipment. Registered scans, you're going to see that accuracy drop a little bit, but you're still going to be incredibly tight at maybe 3 millimeters. Very, very seldom will a single scan ever collect bad data. That can only happen when there's some kind of hardware fault on the scanner. And any reputable company that's out there should be getting their scanners certified at least yearly, and they should have a pretty good quality process in place to make sure their scanners aren't collecting bad data. Where you do see error come in and where you can get some pretty bad error is when someone doesn't do registrations correctly. When they're not doing a workflow that creates a back check. And anyone who's done this for a while should be doing that, and they should know that the registrations are or are not correct, and when it is and is not appropriate to use targets to ensure that they're accurate. So let's talk for a second again, like I alluded to, what used to be okay was taking a tape measure out to the site and manually measuring things. We have a huge record of data that shows that this is completely ineffective. Right, it's in some cases, if it wasn't so costly, it's comically bad. You know, huge things missing, doors missing, windows missing. Pretty much every single dimension is incorrect, and we've checked dozens of projects where someone went out with a tape measure, measured by hand, and drew this up in CAD. We then came back out and scanned the same site, and we see what you see in this picture. Right, and this is on the more mild end, which is every single one of those three windows is incorrect. It's incorrect in multiple dimensions, location, the whole thing. Someone paid to have this building manually field checked, and this is what they got. So this is very typical of what we see. And just keep that in mind whenever you're going out to manually field check things, that I can assure you what you are collecting will not be very accurate. So now let's start talking about what we are collecting. We are collecting incredibly accurate, like we said, millimeter accuracy data. So now all of a sudden for the first time, we have to deal with walls that aren't parallel, floors that are not flat, and what do we choose to do with that when we create our CAD documents? So there's no simple answer to this. It really depends on the needs of the project. If you are on a construction team and you need to verify fits and routings and things extremely precisely, your best bet is to not create a CAD model and simply stay in the point cloud, because you are never going to create a CAD model that is as accurate as the scan data was. It's always going to get worse. On top of that, if you want to get the CAD model done in any reasonable amount of time, it's actually going to get quite a bit worse, because we're going to have to ignore things like walls that aren't parallel and floors that aren't flat. If we try to actually model everything as it is, we're going to be forever in the CAD software dealing with that. But it's important for the project team to understand what's happening. Oftentimes we end up with two sets of data. We end up with the point cloud data and the CAD data, and just know when it's appropriate to stay in CAD and when it's appropriate to go back to the point cloud. Deflection. So when we're talking anything, any kind of framed building, whether it's concrete or steel, we always see this. We have records where we scanned factories and had a large snowfall while we were scanning, and we absolutely pick up the deflection in the trusses under the load of the snow. So how do you want to address this? Do you want to assume that your trusses and your steel beams run flat as designed, or do you want to show them how they actually exist in real life? And then what do you want to do if you did happen to scan while there was load on the roof and things are sloped down? Do you want to correct it or not? And again, this should just be discussed. There is no simple right or wrong answer to this. It's all based on the objectives of the project. So we're going to get into actually working with scan data. That was sort of all of our intro, and now we're going to get into the meat of the presentation, just actually working with the scan data. I think for people out there that are working with scan data, if you take away one thing from this, it's this slide right here. Do not stream point clouds from a server unless you happen to be at a place that has built an entire enterprise around high volume streaming off a server, which almost certainly you are not. Don't connect files from your server shares. Don't remotely access them. Copy them local to your local computer before you attach them to CAD, Navisworks, whatever you happen to be using. All right. This is kind of counterintuitive because for years I think a lot of us have been told never work from your local machine, store all your data on the servers, et cetera, et cetera. That's correct for CAD files. When you're talking point clouds, that's really not what you want to do. And not only that, you're likely to get a visit from your IT folks wondering why you're crashing their network by trying to stream gigabytes of data off of a server share. Okay. Another thing to consider is that perhaps the hardware you currently have is not appropriate. And that's older spinning hard disks on a laptop. This is becoming less of an issue as more of the solid state drives tend to take over on any newer hardware. But if you still have an old drive that's a spinning disk, seriously consider getting a solid state drive. It likely will double your point cloud performance. So a few more points to consider with point clouds. Point clouds are very, very large data sets. I'm sure anyone on the call today that's worked with them knows this. But if it's your first time or the first time you're going to try to put them on a server to be backed up and things, you should coordinate that with your IT department. There's a good chance that a single scanning project is bigger than the typical amount of data that your company generates in a year. They will not be expecting that, and they should plan for that. Plan your work ahead of time so you can copy what you need locally so that you're not trying to pull it all from the network. And those copies, depending on your network speed, they can take a long time. So you try to get them staged up at night, get everything you need for the next day pulled down locally, and you should be good to go. Even though the data is huge, it still works very well in modern CAD packages. So whereas if you were to try to open a DWG that was 5 gigabytes, your computer would no doubt crash. But AutoCAD can use a 5 gigabyte point cloud without any problem at all, even on old hardware. Keep in mind, if you have a large project, something where it's, a million square foot structure, you probably are not going to have a hard drive big enough in your computer, and you're going to want to address that before the project gets underway. And generally, USB, these are the plug-in hard drives. They're very, very slow unless you have a very high-end drive, and you're not going to be pleased with the results you get from using that on a project. You're still going to want it on an internal local drive. Like I said, we used to actually show people how to use point clouds in AutoCAD and Revit. I tend to not even do that anymore. If you're totally new to this and you have no idea, there's plenty of really good videos from Autodesk that show you how to do this, but it's honestly as easy as attaching an XREF and the point cloud simply shows up. And you just draw right on top of it. And you can snap to the points using 3D snaps. I wouldn't recommend doing that. I would shut that off. It's far better to just simply draw on top of the point cloud and visually align things up. That goes back to that discussion we had earlier over accuracy. What do you do when walls aren't straight and things like that? You're going to want to make some decisions. You're not necessarily going to want to snap to these point clouds unless the project really demands that kind of accuracy. We see that in some of the oil and gas work we do and some of the structural work that you really want to hold incredibly tight accuracies and tolerances. In those cases, though, you probably shouldn't even really be using AutoCAD. You should be using one of the add-ins that are extracting that information from the point cloud for you. Same in Revit, okay? You just attach it. Revit is even simpler because there really aren't tools for working with the point cloud. It just shows up and it responds to all the standard Revit commands that you would expect. The one thing I would say in here is to make sure you pin it after you attach it, just so it doesn't accidentally get moved. So we'll get into some kind of use cases to give you an idea of, where to use point clouds and how to work with them. The first one up, this is the easy one. This is the one that is done all the time. This is just creating a very accurate as-built. Like I said, it's very easy to know that these point clouds are correct, to validate that they're correct, and you're going to have a far, far more accurate as-built than anything you could have created using some other technology. Kind of the second most common is in collision detection. Touched on this earlier, Navisworks uses point clouds. You can simply attach it like you would any other file. And you can do all your collision detection, route verifications, all that right in Navisworks. Works really well for kind of hybrid environments. Keep in mind you can, using something like Autodesk Recap, which is free to almost anyone that has any Autodesk product. You can go in and remove portions of the point cloud. So if you have a system that you know is going to be demoed, you can go in and erase that out of the point cloud, save it, bring it into Navisworks. You won't see that system. You can route your new systems through the point cloud. You can embed point clouds into drawings and actually create final deliverables with them. We don't do this too often because the point clouds, again, tend to be pretty heavy. PDF actually has point clouds in it, tends to be very large. You could easily have a single sheet that's 100 megabytes. That sort of defeats the purpose of having PDFs. But where it can help is you will have really high-res images that you can take screenshots of for doing demo drawings and things like that. Right, it's going to give you access to all that data. What we're looking at here in these pictures is the factory floor is existing and the mezzanine is new. And this was done so that a customer could visualize exactly what the space would look like once the new mezzanine was put in. And they were able to actually interact with these images. They were 360. They could spin around, jump between images, really get a feel for what it would feel like to be in this space. Web accessible data. This one is become more and more important as the web accessible things have stabilized. If you're doing your own scans, you should know about this. You can put it up. If you're hiring someone to do your scans, you should request that they make this available to you and your team. Every job we do, we give away 6 months of hosting included. If you need it longer, it's actually pretty cheap nowadays to host it. What this does is it gives you access to the scan data in your web browser. No special software installed. It just works. You have user accounts, you log in, and you can navigate through the data. Very, very powerful for your extended project team to have access to this. Really kind of helps get that data out there. The more people that can access the scan, the better. The less problems you're going to have on your construction site, and the project will simply go smoother. Talked a little earlier about reports. This is one of them. A lot of work's been done in standard compliant floor flatness and levelness studies. There's specialized software out there. If you are in this business, you know what these terms mean. It produces automatic reports. They can save a ton of time. You don't need to be out there doing point surveys. This takes care of it all out of the point cloud, produces very good data sets and formal reports. Okay, route verification, especially if you're doing routing through a complicated space, it doesn't make sense to not scan that and then route your new system through it. And this is one of those cases where you want to stay in the point cloud, not create a CAD model. Creating a CAD model will make this worse. You want to route your systems through the point cloud, validate them in the point cloud, and then if you have to make your customer happy, go ahead and make a simple CAD model to give some context to your new routings, but do not try to prove a route out in a model. So it's just showing some of the stats of a project that we actually did. Routed, I believe these were 16-inch coolant lines. Routed them through a space. It only took a couple days of work, and we're able to prove out the route, suggest a ton of corrections that saved an awful lot of money. The last thing you want to do is have a 16-inch pipe not be able to fit through a space correctly. This is one of the scans from it down in the pump room where the line started. This is also a good example we talked about earlier about black and white versus color. What you're looking at here is grayscale data, which means no photographs were taken. This is the density of modern scanners for anyone who's not familiar with that. This is the full resolution data from a scanner. Another thing we're doing more and more lately is construction validation. So especially on projects that have, unique contract types like IPD, where everyone needs to be on the same page, everyone needs to build to their model, and anyone who's not building to their model needs to be called out. Very important because everyone has shared risk. So this comes in handy for that. We can come in, we can scan the space, and we can quickly verify whether or not people built what they said they were going to build. We can take a snapshot of their model that they said they were going to build, lay it over the point clouds, and these can happen depending on the square footage, same day. So you can come out, you do the scan, you merge the models, and then everyone meets, you sit down, and you go through it and review whether or not everyone was fulfilling their obligations. Pre-pour verification, very good to have done before you pour concrete. Make sure that all your piping and everything is laid in the correct locations and that you have a record of what you're about to bury. So lastly is kind of tying all this stuff together, what we would call kind of the VDC, the virtual design and construction workflows. We want to kind of tie scanning and modeling and the whole process together in order to make sure that what we do is going to work. right? And whereas before with like manual field checking, you could go out, you could check things, you could be pretty sure it was going to work, but everyone still had contingencies built in because everyone knew that the data we were collecting was pretty soft back then. Now, if we look at this and this is a furnace, if we know that this furnace is going to fit, we can be absolutely sure that it is going to fit. There is nothing in this point cloud that is not correct, that is missing, that got overlooked. As long as we do our work correctly, this is going to work. It is going to fit in here. In this case, this project involved raising the truss to make sure that we could lift out some soot tubes out of the furnace and make clearance. And we could make sure that absolutely that was going to work. Same thing applies to off-site fabrication. Right, in the past, no one would really dream of doing off-site fabrication for large MEP installs. Right, the ceiling space was just way too complicated. You wouldn't know what was really going on. Now we can do this entirely off-site. We can prefab everything and have it brought in. Right. I'll ask you kind of what the effects of this are on project budgets. These are based on real numbers from a partner of ours that we worked with for many, many years. Did hundreds of scan projects with them. And what we're seeing here is sort of the cost of field orders versus the base contract as we move from traditional 2D workflows where you're really not sure if what you're collecting is correct into sort of basic 3D, which would be scan or model or manual field check and model, right, which is still better than 2D, into what we call advanced 3D, which is the fully integrated or mostly integrated, in this case was design build contracts. And we basically set field orders to almost zero. So the effect is the base contract goes up, but field orders essentially can go to zero on projects.